Hi, today at the algorithm seminar we are hosting Krzysztof Potępa.
Hi.
Krzysztof, please start.
Hi, I'm Krzysztof. I'm currently pursuing masters at Jagiellonian University, and I'm here to talk about my paper, Faster Deterministic Modular Subset Sum. Okay, so let's start. I'm sure everyone's familiar with the subset sum problem. We're given a multiset of integers x and the target integer t, and we're asked to decide if there exists a subset of x that sums to the target integer t. And we're going to consider a variant of this problem, the modular subset sum problem. Basically, we consider the sums modulo sum integer m. And we're actually interested in algorithms that return all possible subset sums. We're not given a single target integer t, but we want to compute all possible integers t. And we'll assume that that n is order of m. This is because first of all we can do a simple reduction, so it holds, and it's easier to think about complexities later. We don't need to think about n. Let's review some what is known about this problem. The first one is the classic dynamic programming algorithm that everyone learns at university. There were recently a lot of new algorithms for this, and the last three are interesting for us. All of them actually work by reduction to some string problem. We'll see what string problem it is, because we'll do the same actually. And actually, these two papers came out independently in August last year. Okay.
Can I ask one specific thing? Yeah. Since we are actually looking into polylogs, what is the precise model? Are we talking about RAM machine or?
Yes, RAM machine.
Okay, thank you.
I mean, we're not gonna use any tricks to get anything faster here, but okay. So the difference between these three algorithms is that they actually just use different structures, data structures, to solve the problem. And what we're gonna do is we're gonna develop a simple data structure for this string problem, and then provide two algorithms based on it. The first one randomized, m block m, so its complexity is the same as the one of Cardinal and Diacono. And the second one is deterministic, and it works only slightly slower than the randomized one by a factor of inverse Ackermann. And our algorithms will be actually offline, and they won't be output sensitive, while these three algorithms are. So that's small deficiency, but we're getting a faster deterministic complexity here. Okay. So first, let's recap the classic algorithm that works in NM time. We define Sk to be a set of all subset sums attainable if we only consider the first k elements, and we can provide a recursive formula for the dynamic programming. S0 just contains 0 and nothing more, and Si, if you want to compute Si, then we need to look if we want to take the ith element or not. So we take either Si minus 1 or Si minus 1, where we add xi to each element. I'll use this notation for this. And the classic NM algorithm just computes these sets directly, each in time linear in M. And we basically want to somehow simulate it faster. So let's define Ci to be set of new attainable subset sums after adding the ith element. That's the difference between Si and Si minus 1. We can rewrite it like this. So we want to compute these consecutive sets Ci in time dependent only on their size, not in time linear in M. And it seems hard to do this, to compute this set Ci directly, but there's a nice observation that we can actually compute the symmetric difference instead. Because the size of symmetric difference of these two sets is just twice the size of Ci. This is because we can rewrite symmetric difference as sum of these two sets, normal differences, and they have the same size. It's quite easy to see. And okay, so what can we do? We can just compute the symmetric difference, Pi, and then reduce it to the set Ci. Just ignore the elements that we don't need. And why this observation is useful? It turns out that this problem has a nice interpretation as a string problem. It's easier to look at it this way.
Can I ask one more question about the previous slide?
Yes.
Is this and then reduce it to Ci? Is this something I should immediately see, or something that you're going to explain in a second?
Ci is a subset of Di.
Yes, but how do I extract it?
You don't. You just iterate over Di and ignore elements that are not in Ci. Because, like the observation above, the set Di is just twice the size Ci. So we don't break complexity if we iterate over the whole Di set.
But how do I know which element is? Am I missing something here?
We can actually add the whole set Di because.
Because there are no bad elements there. Okay, right.
Yes, there's no bad elements.
Sure, of course.
I just meant we may find there are some elements that are already in Si-1 set. But
we are holding Si-1 in hand, so it's safe.
But okay, also it's like checking if the element is in Ci. You can do this in a constant time.
Yes. Okay, so let's continue. So we can interpret this as a string problem. So first, let's define characteristic vector of the set Si. I mean, just a binary string. Let Si be a binary string of length m, such that we have 1 at jth position, if and only if j is in the set Si. We use here zero-based indexing. It's nicer that way here. Typical characteristic vector of set. And let's also define cyclic shift of string. I'll use this notation, plus k in the upper index. So by this I mean a cyclic shift of S to the right by k positions. And now we can observe that the set Di, this symmetric difference, is just the set of positions where the characteristic vectors of these sets differ. Okay, I don't know if it's clear, or should I somehow show it?
I think I'm the slowest one here, and I see it, so I think it's safe.
Okay. All right. So we can continue now. So if we had a data structure that maintains a binary string S under two operations, the first one is changing character, the second one is finding all positions where S and its cyclic shift differ, then we could provide, then we can write a simple algorithm for the subset sum. We just simulate the Bellman iterations. So we start with the set that contains only 0. A is the data structure built for the characteristic vector of the starting set S. So it's 1 and all zeros, because we have only 0 here. And then we iterate over elements. We check, we find all positions where the characteristic vector and its shift by x to the right differ, and add these elements to set, update, and update our data structure. And if we do this, okay, and what complexities do we want for these operations? We want set to work in some polylog time, for example, and the diff should work in time dependent on the output of diff. For example, if it returns d differences, then you should work in some d multiplied by polylog time, something like this. And if it works like this, then we get algorithm that works in polylog time, because we always change 0 to 1 here, and the symmetric difference is just twice the size of normal difference from the previous observation. So everything works. So how do we go about this data structure? What options do we have here? The first option is just to use some powerful dynamic strings data structure. I mean, a structure where we can freely concatenate, split, make equality checks between strings. Such data structures exist. And if we want a deterministic time, then we can use some structures of Modular and get polylog time. And that's one of the recent results. They just use this data structure. If we want randomized time, then Cardinal and Diacono provided a new simple data structure, data-dependent trees, that allows randomized m log m time. There are also some more involved structures that do the same, but they simplify the algorithm.
Okay, can I get some intuition? I mean, let's say I'm interested in randomized and like arbitrary polylog setting. Okay. So I can just maintain rolling sketches and do LCP queries, right?
You mean rolling hashes, right?
Rolling hashes, yes. Rolling hashes and do LCP queries there, right?
Yes, we can
and
keep
I
some
would
trips.
Get, yeah. M polylog M time. Okay. Wow, cool.
Yes. Okay, and perhaps the simplest approach is just to use segment tree with hashes. Instead of the whole dynamic strings data structure, we can build a segment tree over the characteristic vector. And we can implement it in mlog squared time, and we'll see how it's done in a second, because we're actually gonna optimize this approach. Okay, so how does the approach with segment tree works? Okay, first of all, we double the string, the characteristic vector. So now every cyclic shift of string S is a substring, and we build a segment tree over it. Every inner node contains a hash of underlying string, and what we can change any character in log m time by updating the path. We can check equality of two substrings in log m time, because we can get hash of any substring in log m time. And we can do LCP query in log squared time by binary searching for the answer and checking the equality. And with LCP query, we can simulate the diff operation, finding the first difference, the second difference, and so on. So if we use this, then the bottleneck is the LCP query, which runs in log squared time, and we would get that mlog squared algorithm or modular subset sum if we were to use this. So we want to somehow optimize the LCP query. Okay, so what's the idea? Let's see. Suppose that we want to find LCP of these two substrings. In this case, we can actually do this in log m time, because these substrings have the same tree structure. These are actually base intervals in this segment tree, and we could do the so-called binary search on tree. We can just take roots of both these intervals and descend to the first difference. First, we compare hashes here. If they are equal, then these strings are equal with high probability, so there's no difference between them. Else, we look at left children. They have equal hashes, so the difference is on the right, so we turn right. And then we turn left, and we find difference, so LCP is 2 in this case. And this would work in log m time because height of the tree is log m, obviously. But this won't work if we have a situation like this. We want to compare substrings like this, because now now if we decompose them into base intervals, these segments are different. We can directly compare this segment of length 2 with this segment of length 1, and we'd have to subdivide it further, and pessimistically we get some. I'm not sure, but it's bad. It's definitely not log if we subdivide it further. So how to fix this? What if we had? What if we have a second tree that's built over a specific cyclic shift of the string? For example, here we want to compare this substring with this substring, and suppose we have a tree that such that this second substring is a prefix of the second tree. Then, if we want to find LCP of these two substrings, we can just compare. We can do this by descending from roots of both trees. And in this case, it's the leftmost leaf. And we have LCP of these two strings. It's 0. But obviously, in our algorithm, this offset changes. We want to do queries for different offsets for this second substring. The first substring is always a prefix, but the second one changes. So we can't keep one tree and work with this. We need to somehow transform it, and that's the basic idea behind our structure. We're going to keep. We're going to transform the second tree during the algorithm, so that there is a point in time where every substring, we're just going to see every cyclic shift of the characteristic vector in this second tree. Okay, maybe let's see how it's done. So we define, I'll call this data structure shift tree. Shift tree maintains a binary string of length that is a power of 2. That's important. We'll see why in a moment. And we support 3 operations. First is set. We change character. LCP finds the longest common prefix between 2 shift trees, one shift tree T and some other shift tree Q. And the interesting operation is the shift. We want to cyclically shift the represented string by some positions to the right. And we implement this structure as a segment tree with hashes. So set is easy to implement in log n, as before. LCP is just I've shown before. And the interesting part is the shift operation. Okay, so let's see how to do shift.
So first, what complexity do you expect from the shift operation? Is it?
Yes, I'll show it on the next slide because it's
okay.
Set and LCP will work in log n time. Shift, we'll see.
So I bet on amortized constant or something like this.
Amors.
We will see in a second. Okay.
So first, let's consider a shift by power of 2. We want to shift the represented string by 2 to the power of I. So what's the naive approach? Naive approach would be to simply shift values in leaves and then recalculate all the hashes. But we can notice that if we shift leaves by the power of 2, then we actually shift some subtrees by 1 to the right. Okay, so instead of shifting values in leaves, we take links in the tree on appropriate level, and we shift them by 1. And now we can notice that all these lower levels have already good hashes. They were computed before. and we just need to update hashes on the higher levels. So what complexity such shift has? Number of these nodes over the complexity is dependent on number of these nodes on the higher levels. So if we sum it up, it's m divided by 2 to the power of I. So basically, if you want to shift by 1 or any other odd number, then the complexity will be linear of shift. If you want to shift, for example, by 2, m divided by 2, then it's constant. We just need to swap these two children. And it turns out that it is enough, because we'll later show how to order elements, input elements in modular subset sum, so that this amortizes nicely. Of course, we can. I've shown shift by a power of 2, but we can generalize it to any multiple of power of 2. So if we want to shift by x, then the complexity is m divided by 2 to the power of j, where j is the largest integer, such that we have power of 2 that divides x. Okay, so that's pretty much all there is to this randomized variant of shift trees. The space is linear. Set works in log m. It's standard set as in segment trees. LCP works in log m because we can now descend from roots of both trees, and shift works in that weird complexity. And I said before that we need the length of string to be a power of 2. That's because this trick with changing links would break if it's not a perfect binary tree. So we need the number of leaves to be power of 2. But
I'm missing something. Why are we taking the largest j?
Okay.
If you need to, I mean, let's say you do a shift by 17.
And it's odd number, so it's linear.
So then it will be m divided by 16, right?
No,
m divided by 1. Okay. Okay. Now I see. It's the lowest odd bit.
For example, if we take 20, then we have 20.
Lowest odd bit. Okay.
Yes, lowest odd bit. That's right. We can actually, I didn't say it before. It's we can actually implement this without storing these links, but that's just a technical thing, and it has really nice implementation. This whole shift thing. But we'll skip that. Okay. So let's see how to use this data structure to solve modular subset sum. So first, generic algorithm. So how do we do this? Now we keep two data structures, T and Q. Both are built for the characteristic vector of S. And T stores just the characteristic vector of S, while Q stores some cyclic shift of this characteristic vector. More precisely, we'll keep invariant that Q is always characteristic vector of S shifted by delta to the right. And we now iterate over all elements. We first change shift of the tree Q to match X, and we set delta to X. So we shift by difference between X and delta. It's always a difference between two consecutive processed elements. Unless we process the first element, then it's just X minus 0. And if we set this shift of data structure Q like this, then we can just find differences between T and Q. And these are our new subset sums that are possible. So we add them to set S and update these two trees. Okay, and if we implement it like this, then we get m log m m log m plus the complexity of shifts time, because the diff is implemented using LCP. We can simulate it using LCP and set operations. So it works in log times number of differences. Everything here works in m log m, basically. Only the shift is interesting, is a bottleneck here. We want to make it work fast, all the shift operations. So the total complexity of shifts depends heavily on the order of processing the elements. If we process in random order, then it's still quadratic, for example, I believe. So the question is, in what order should we process the input to get nice complexity? And the answer to this is to process them in bit reverse and permutation order. What do I mean by that? Suppose we have suppose that input we have as input all elements from 0 to 7. Let's look at the binary representation of these numbers. We want to sort them by reverse of this representation. So we get order like this, and we want to process elements in this order. And I say that it's good. What's the intuition behind this? We basically want the
But this is not dependent on m.
It is dependent.
Okay, so you assume that m is 2 to some power of k.
Yes, I forgot to say. For now, we assume that m is a power of 2 because we want to use it in shift trees, right? We want to use shift trees directly. It's an easy fix. We'll come back to this later. Okay. For now, we assume that it's power of 2. Okay. Why this order is good? Basically, shift operation works the worst if the lowest non-zero bit is small, right? So if we look at we always shift by difference between two consecutive numbers. Pessimistic case is that all numbers are present. If we remove some number from the input, then it's not worse, the amortization. Shift from this number to this number is better than shift from this to this and then from this to this. So we can consider the pessimistic case where all numbers from 0 to the power of 2 are present. And now, if we use that order, we can notice that the least significant bit changes only once. And that's nice because this is the case where shift works in linear time. If you look at the second least significant bit, it changes only 4 times or 3 times. And the complexity of shift here is divided by 2, so it can be. We can see that it amortizes. We'll show it more in a second. Okay, so let's look at this. Let's look at two consecutive integers that are on input, and let's assume that this is the least significant bit that changed. If we look at shift that transforms the 3q from this first offset to the second offset, then it's the difference of these two numbers. So all these bits are 0. So the complexity of shift depends on this lowest bit that changed between these two numbers. And now we assumed that, excuse me. We assumed that all numbers from 0 to power of 2 are present. So actually, the prefix of this always looks like this. If we look at the reverse representation of this, then difference between reverse between these numbers reversed is 1. So basically, what happens here is, if you want the next number after this, we add 1 to the leftmost bit and carry it to the first 0. So the prefix always looks this way. We have some amount of zeros, then 1, and the previous number looks like this. So,
so as I understand, the key idea is not that you are always creating a new shift by k from the original string, but you are maintaining on a site a shift by k, and you just update a k.
Yes.
And by changing the shift value, you are okay. That's a really cool trick.
Yeah, we always shift from the previous number we processed.
Do I understand correctly that for every bit you will get like the linear total cost?
Yes. So, okay. So if this is the lowest changed bit, then this whole prefix is fixed. So number of shifts that for which this is the lowest bit that changed is dependent on number of combinations that we can fill this suffix. So if this is position j, then we have 2 to the power of j options here. So now if we sum over all bits, we get something like this. And this is exactly m log m k times m. We get m log m amortized complexity for shifts. So, and that's it. Now if we plug it into algorithm, we get m log m time randomized. It's randomized because we use hashes for now. And there's this one thing that we left. We required that m is a power of 2, so we can use shift trees directly. So it remains to answer question how to handle cases when it's not a power of 2. And that's easy fix. We just want to double the string and pad it with zeros, or more precisely, we put zeros between those 2 copies of strings. And now we can see that the cyclic shift of s of the original characteristic vector is prefix of string defined like this, as long as k is in the nice range. So if we plug it into the algorithm that I've shown before, nothing breaks, complexity doesn't break, and it works for any m. So we get m log m randomized algorithm, and that's the first part of the paper. Now we can move on to how to make it deterministic, because it turns out it's easy to make this data structure deterministic. We won't need any changes to the algorithm now. We just need to change something in data structure to make it deterministic. So we can notice that why do we need hashes in this structure? We need them to compare if strings represented by some two nodes in the tree are the same. We don't need to compute hash of any substring. So our hash function doesn't need to be associative, actually. We can just we can think of it like we're hashing subtrees, not strings below this. So what we can do is we can replace the hash function with any injective function that maps hashes of children into hashes of parents. And we need to keep those values small. So we just generate this hash function on demand and store values in BST. And that way we get m log squared time deterministic algorithm. We could use hash map instead of BST and get m log m time, but that would be randomized. The difference between this and the previous algorithm is that this would be Las Vegas. It always returns correct answer, but it doesn't necessarily work in m log m. But it turns out we can do better than m log squared. And the idea is to replace hashes with something I call tags. We'll see what it is in a second. On each update, instead of calculating hash, we create a new tag and put it in node. So it's like there may be multiple tags that are associated with the same string, and we will somehow propagate which tags are equivalent lazily during the LCP operation. Okay. To maintain this equivalence relation in tags, we just use disjoint set union with one additional operation, delayed operation. This is done to maintain linear memory complexity. We could ignore this we could ignore this operation and get mlog m memory complexity. Okay. The idea is that we maintain such an invariant. If we have two tags, x and y, then if x and y are in the same set in disjoint set union, then strings represented by these tags are equal. But this invariant doesn't hold in the opposite way. So for example, if we do set operation and we update nodes on path to the root, then we just create a new tag that is in singleton class in this disjoint set union, and put a new tag like this in every node on the path to the root. And later, during the LCP operation, we will join these sets in our disjoint set union to make it amortize. Okay, so let's see how LCP works, because that's the interesting part. Here we have example where we have two shift trees. I marked with colors the sets that contain tags associated with nodes. For example, here we have, in this node, we have tag that represents string 10, and in this node as well. And they have the same color, so they are in the same set in disjoint set union data structure. Intuition is that algorithm already knows that these tags represent the same string. But for example, here we have also tag that represents 10, but it's in different set for now. And the algorithm doesn't know that this tag represents the same string as this tag, for example. In the same case is here. We have tag that represents 1001. And here is the same, but we don't already know that they are equivalent. So how do we proceed with LCP? We want to find LCP of these two strings. We start at root, at both roots. We see that tags are in different sets. So it means that maybe there's a difference somewhere between the strings, maybe not. We don't know yet. We need to proceed recursively on children. So we look left, we turn left. We see again that tags are in different sets. So we need to again proceed recursively. We look at left children of these two tags. And what do we see now? They are in different sets. So we don't know if there's a difference between the strings or not. But if we look at left and right child, then we see that these strings are actually equal. So there's no difference between these two strings. So it means that these tags are equivalent. So we can just union these two sets in find union. And now this tag becomes red. And this whole call here was unnecessary. We didn't need to go here to find the LCP. So we go back. We now look at right children. They again, this time they are in the same set. The tags represented by these two nodes. So we know that these two tags are equivalent because the children are equivalent. So again, we union these two sets. This becomes green, and we go back. Now we go right. We see that left children are equivalent. So we go right. and we find the first difference here. And what happens if we invoke LCP the second time after this operation? We see that these left children have equivalent tags, so we don't need to go there anymore. We just go right and straight to the place where these two strings differ. So if we look at this LCP operation now, what's the complexity of it? We need log m time to descend from root to the place where there really is that difference between strings. Plus, we may have some additional calls that were unnecessary because strings were equivalent. But each time such call happens, we join two sets in find union, so this will amortize actually. We could analyze this using some potential method, but let's see quickly how it works if we use this in modular subset sum. So first we can bound a number of created tags during the whole algorithm. We maintain two shift trees in modular subset sum, so initialization creates m tags, to order of m tags. Now all set operations produce in total m log m tags because we have at most m sets, and each produces log m tags because it updates path to the root. Shifts amortize to m log m, number of updates, number of node updates in all the shifts amortize to m log m. So we again produce m log m tags in total. So in total we created m log m tags during the whole algorithm. Now, if we look at the redundant calls, then as I said before, every redundant call joins two sets in DSU. So it means that it decreases the number of sets in DSU by 1. So it means that number of redundant calls cannot be greater than number of created tags, and this is m log m. So we see that LCP amortizes to m log m. All LCP operations amortize to m log m, and we get the final deterministic complexity m log m times alpha m. This is from find union operations, and space is m if we delete unused tags appropriately in find union. We can do that. All right, so that's all. That's all there is to the deterministic variant. And I have a few open questions. So first of all, can we get output sensitive or online algorithm with this approach? Obviously, this algorithm is offline. We need to order elements appropriately to get nice complexity here, so it's obviously offline. And the question is, can we somehow make it online? I don't think so. With the approach of shift trees. And the second question is, can we make this output sensitive? So about output sensitivity, it's quite easy to make space complexity output sensitive, because when we have the shift trees, we can just unwind them dynamically when we visit nodes, and that would give us output sensitive space complexity. But there's a problem with time, because the shift operations will still amortize to m log m, not an output sensitive complexity. And I thought about it for quite a while, and I don't know how to fix this. And all these recent algorithms have these both of these properties actually. So yeah, we pay these properties for getting faster deterministic algorithm. Second question is, we still have the Ackermann in complexity, in deterministic complexity. So the question is if we can get rid of it somehow. Maybe we can see some better amortization, because it's some better amortization here. And actually, maybe we can do faster than m log m. It's been proved that as long as strong exponential time hypothesis is true, then modular subsystem cannot be solved in faster than linear time. And we have currently m log m algorithm, so maybe we can do faster than that. We can do better than that. And that's all I have for today. So thank you. If there are any questions, I'm here to answer.
I mean, for me, the most natural question is, I think, the third one. I mean, is there any reason to believe that m log m should be the correct answer? But I have absolutely no intuition here on this. I don't even think if we have in theory the tools to be so fine-grained that to be able to distinguish between pure linear and m log m. I don't know. Maybe Bartek knows more.
Depends on the model, right? I mean, yeah, but in RAM, I've never heard about something like this. So it's usually easier to just show a better upper bound.
Lazy approach.
Very lazy. Yeah, so I'm wondering, because this algorithm is actually, it's really elegant and simple. And these other two results from 2020, they appeared on SOSA, actually. So
Yes.
So is it like you have even simpler algorithm than
not entirely. This, I mean, this
there should be SOSA squared conference.
Yeah, something like
for simpler algorithms that were already published on SOSA.
The m-log squared algorithm here was actually just using segment tree of hashes. It's the basis for our algorithm, pretty much. We optimize it. So it's simpler, I believe. The other two use dynamic strings data structures. So yeah.
My impression should be that you are using, in a deterministic variant, you are using this union find in such a specific way that there should be a way to get rid of this Ackermann. But I mean, what do I know?
I thought about it. I don't know how to do this yet, but maybe that's a way.
But the technique is pretty general, right? Like you want to, like this part of the paper might work not only in this particular problem, right? So this is pretty nice.
I like it. I mean, I like this whole approach. It's really pleasant to see such a simple ideas amalgamated together.
I've already heard that it's a cute algorithm from someone.
Yeah. Okay, so if there are no more questions, I will just stop the recording.